Good afternoon, everyone. I hope the heat is not treating you too bad. So I'm pleased to be here as a representative of STMicroelectronics to present a solution that we have developed together with our partner company, Newtwen. To build a real system, to make a proof of concept, for sure we need to start from existing elements. And we know we all need software, we all need hardware, but we also need ecosystem that can help, particularly new companies, to develop new solutions. That's why we have partnered with Newtwen using our BMS solution, where you can see a node solution with a transceiver solution for connection of nodes in an isolated way. And we have built a battery pack, a simulation of a battery pack, where thanks to the technology Newtwen has provided, we were able to not only use the 5 temperature sensors that are provided by the IC, but also combine this data with other 10 virtual temperature sensors, which a digital twin running in the same microcontroller that is already controlling the BMS is able to compute, thus delivering what? A better estimation of the state of charge of the system, but also a better sense of placing, because thanks to the Newtwen algorithms, we can also compute where to better fit the 5 sensors that we have together. And this was the starting point to build solution together, because then, after that, Newtwen has developed a new solution for us. To you, Scott.
Excellent. Thank you very much, Max. My name is Scott Cobble, and I'm the Chief Operating Officer of Newtwen, and it's a privilege to be here with you today. So as Max just described, this was a demonstration that we presented about 3 months ago, and since then we've gone even further with this application. And in particular, what we've seen is that the state-of-the-art in battery management system technology just isn't adequate to support the growth of e-mobility and also of the second life battery market. So, as many of you are aware, is that the asset of an electric vehicle includes over 30 to 50% of the cost in the battery itself. So, within that battery pack, you have a BMS control that does not adequately account for aging mechanisms in this system. So that's things like plating or aspects that definitely degrade over time, but that current methods aren't adequately able to measure or model. As a result, engineers have no other choice but to oversize and overdimension the pack, and then over time this clearly is not the most efficient solution, and it's not cost effective either. Moreover, state of health information does exist, but there's global consortiums that are working on standardizing this metric, and what we've seen so far are data-driven methods. However, transmitting data to the cloud to store, to process, and interpret are very high. And moreover, these state of health estimates are very conservative, and this leads the entire asset of the battery to be undervalued. So what we see is that physics-based models are able to provide accurate predictions over a wide variety of operating conditions because they proceed from the physics themselves. So going up beyond simple time series data of voltage and current, what we're able to do is bring an embedded digital twin. So this is a physics-based model that runs in real time inside the electronics hardware already in the device. So what we've done is we've encapsulated years of research and development into what we call the digital twin factory. Years ago we began with electric motors as well as power electronics, and now we've moved on to batteries. And so what this approach is able to do is it incorporates the geometric design of materials, and in particular the electrochemical properties of the specific cell and chemistry. From there we're able to utilize our techniques to maintain accuracy of very FEM-based, partial differential equation-based models, DFN, to bring those down to a level that is very computationally efficient, such that these physics-based models can run in real time. And what does this provide? It provides much better estimates for temperature, as well as for things like overpotential, things that contribute directly to aging mechanisms. So overall, this results in a reduced battery size to achieve the same performance. There's a better estimate of state of health, an optimized usage of cloud infrastructure when it is necessary to pass data for fleet management, And finally, it enables a battery passport that's much more accurate and physics-based. So legislation just was released a few days ago at the European level, and we're glad to be part of this effort. So what does this all mean at the end of the day for a battery pack? It means that over the life of the asset, by incorporating this physics-based, real-time embedded digital twin, you're able to use a control strategy that maintains the life of this battery pack and increases the economic value in years to come. So as we look at the battery second life market, you see from less depreciation, improved warranty, and ultimately enabling this battery passport. It's worth mentioning that Newtwen's physics-based embedded digital twin technology isn't just about batteries, but it also involves electric motors, power electronics, and more applications in automotive as well as in industry. And we're really excited to share with you all today this demonstration, our latest application, and thank you very much for being here. And my name is Scott Cobble, and very happy to represent Newtwen today. Thank you.
We invite you to come at our Newtwen booth to learn more about all these solutions and what we can do in thermal management. Thank you very much.
Thank you very much, Scott and Max. So,